వెరోనిక ఏం చేసావు ఇప్పుడు? ఎవరు నువ్వా? నేను ఎందుకు ఆపిన సౌండ్? Good morning to all. Am I audible? Just mention in the chat box. Am I audible? I don't need that. Good morning. Am I audible? Just mention in the chat box. Yes or no? Yes. Okay.
ఎంత కాస్ట్
Okay, I'm going to start the class. So current gain parameters of bipolar junction transistor. So bipolar junction transistor current gain parameters are alpha, beta and gamma. I will just expand the screen. Current gain parameters of this bipolar junction transistor are alpha, beta and gamma. Okay, it's okay. So alpha, beta and gamma. This is it. Alpha, beta and gamma. They are the current gain parameters. So these parameters alpha, beta and gamma, they describe the relationships between currents at different transistor terminals. Okay, so we know the transistor terminals, bipolar junction transistor terminals. The bipolar junction transistor terminals are, if there is any disturbance, you can inform me. Okay, the bipolar junction transistor terminals are emitter, base and collector. So we know types of bipolar junction transistor. They can be either PNP type or NPN type. So this is PNP type bipolar junction transistor. This is NPN type bipolar junction transistor. Either it is PNP or NPN type. The terminals are emitter, collector and base. Three terminals: emitter, collector and base. Okay. So if we want to determine the current gain parameters, which are alpha, beta and gamma, okay, so we can determine for this BJT, okay, bipolar junction transistor. So if we know the terminal based using the terminals, okay, so using the terminal currents, actually the currents at the terminals, how to determine the terminal, so not terminal, but how to determine these parameters, let us see. Okay, so by using the terminal currents, current flowing through the emitter, collector and base, using those current values we can determine the alpha, beta and gamma. These are the current gain parameters. So let us see the first one, that is alpha, common base current gain. Alpha is known as common base current gain. Alpha is known as common base current gain. So it is the ratio of, I will take the laser, it is the ratio of collector current to the emitter current. Okay, for the what to say, BJT, which has a common base terminal. So what is meant by common base terminal? So I'm showing you, no, when laser is there I can't change the slide, it's a better pen. Yeah, so you can see this diagram here. So in this diagram, one second. In this circuit diagram, if you observe here carefully, this is our BJT. Okay, emitter, collector and base terminal. Okay, so this is our BJT, bipolar junction transistor. Okay, so this is our BJT. Okay, this is our input V in, this is our output. Okay, so if we observe this base terminal is common to the input as well as common to the output. Okay, so if in the given circuit, if the base of bipolar junction transistor is common to both input as well as common to both output, then that BJT can be called as common base BJT, or you can categorize BJT, bipolar junction transistors, into three configurations: common base configuration, common collector configuration and common emitter configuration. Okay, so if it is common base configuration, base will be common to both input and output, as I have shown you in this diagram. If it is common emitter configuration, I will show you that also. This is common emitter. If you see here, this is BJT. Okay, this is BJT. Here, emitter is common to both. This is our input V in. This is our output V out. Emitter is common to both input as well as to the output terminals. That's why this circuit, you can call it as common emitter configuration BJT circuit. Okay. Next, common collector. So see here in this diagram, this is our BJT. Okay, so this is our emitter terminal, this is our base terminal, this is our collector terminal. Okay, emitter, base and collector. So if we observe here, the collector terminal is common to both input. This is our input terminal, this is our output terminal. So it is common terminal is common to both input side as well as output side. So this sort of configuration is known as common collector configuration. So BJT has three configuration. Okay, that is also available here. Somewhere I have written. BJT has 3 configurations. I will show you that I have written somewhere. BJT, bipolar junction transistor, has bipolar junction transistor has 3 configuration: common base configuration, common emitter configuration, common collector configuration. Common base configuration means the base will be common to both input and output terminals. Common emitter configuration means base will be common to both input and output terminals. Common collector configuration means collector will be common to both input and output terminals. Okay, so let us go back to our main concept, that is current gain parameters of bipolar junction transistors. So one of the current gain parameter is alpha. Okay, one of the current gain parameter is alpha. Okay, so alpha is the common base current gain parameter. Okay, common base current gain parameters. Common base means what? Base will be in this circuit. You can see base will be on this pen. Base will be common to both this base. It will be common to this is our BJT, whose terminals are emitter, collector, and base. Base will be common to both input as well as output. Okay, base is common to both input as well as output. Okay, so alpha is determined for common base configuration circuit. So alpha, what is alpha? Alpha is the common base current gain. Alpha is the common base current gain. So alpha, it is the ratio of collector current. It is the ratio of collector current to the emitter current. For what? For the common base terminal. Okay, for the given circuit. Okay, so alpha is the ratio of IC by IE. You can note it down in your notes. Alpha is equal to ratio of collector current by emitter current, whose alpha value it will be almost greater than or equal to 0.9 and always less than 1. So 0.9 and 1 are almost nearby values. Okay, so we can say that alpha is always closer to 1. Okay, so common base current gain value is always closer to 1. Okay, so I hope you have understood. Now let us see the another current gain parameter. The other one is beta. So what is beta? Beta is common emitter current gain parameter. Okay, common emitter current gain. Common emitter current gain parameters means the emitter will be common. BJT emitter will be common to both input and output. Okay, so for such circuits in which BJT is connected in such a way that emitter is common to both input and output terminals. So beta is a common emitter current gain parameters. Beta is given as ratio of collector current to the base current. Okay, ratio of collector current to the base current is nothing but beta. So beta is what? It is a common emitter current gain. So this beta value usually it will vary from 20 to 200, means it is in between 20 to 200. See, numerator is current, denominator is current. So this current gain parameters will not have any units because numerator is current. What are the current value in milliamperes or amperes in the numerator and denominator? Ampere amperes will cancel each other. Okay, so if the units of numerator and denominator are same, then those units will be cancelled, and the parameter whatever you are determining, those parameters will not have any units. Okay, so common emitter current gain, it is a ratio of what? Collector current to the base current. When what? When the emitter terminal is common. Sorry, this pen. When the emitter terminal is common. So beta is determined for the circuit in which BJT is connected in such a way that its emitter is common to both input and output. Okay. So let us go for the next parameter, that is common collector current gain. Okay. Just now we have seen common base. Next we have seen common emitter. Next common collector. So you can see here, this is emitter terminal. It is not shown in this diagram. That's what I'm writing. This is base terminal. And this is collector terminal. Okay. And this collector terminal is common to both input as well as output. Okay. So for such circuit, we can determine the common collector current gain. So it is the ratio of emitter current, okay, emitter current to the base current, So gamma is equal to IE by IB. Gamma is equal to what? IE by IB. So common collector current gain is the ratio of emitter current to the base current when emitter current to the base current when the collector terminal is formed. I hope you might have already written. Okay. Hope you have written. So I'm just going for the relationships between alpha, beta, and gamma. Next, relationship between alpha, beta, and gamma. Okay. So what is alpha? Alpha is the common base current gain. Beta is the common emitter current gain. Gamma is the common collector current gain. Okay. So are you able to follow? Or if there is any confusion, if you want me to repeat, you can mention in the chat box repeat. If you are able to follow or not, you can mention in the chat box whether you are able to follow or not. Okay, so now let us see the relationship between alpha, beta, and gamma. Okay. For that, what I am going to do is I am going to take this PNP bipolar junction transistor. Okay, so in this PNP bipolar junction transistor, if we observe the currents, terminal currents, emitter current, base current, and collector current in this circuit, if we observe the emitter current, base current, and collector current, emitter current is entering, base current is leaving, collector current is leaving. Isn't it? Emitter current is entering, base current is leaving, and collector current is leaving. So we can say that IE is equal to IB plus IC. Okay, you can apply Kirchhoff's current law here to this BJT. Okay, to this PNP BJT, and we can get a relation by applying Kirchhoff's current law. We can get a relation between this emitter current, base current, and collector current. So emitter current IE is equal to IB plus IC. Okay, similarly, if I take NPN transistor, okay, if I take NPN transistor, if you observe, emitter current is leaving, base current is entering, collector current is also entering. So here base current and collector current both are entering and IE is leaving. So I can say IE is equal to IB plus IE is equal to IB plus IC. IE is equal to IB plus IC. Whether it is PNP or whether it is NPN, by applying Kirchhoff's current law, you get the same relationship. So to get the relationship between alpha, beta, and gamma, what I am going to do is I am going to apply Kirchhoff's current law to the transistor terminals, and you have to write down the derivation. Whoever is attending the class, just write down the derivation. So by applying Kirchhoff's current law at the transistor terminals, what do we get? IA is equal to IB plus IC. So consider it as equation 1. Here what is IA? IA is the emitter current, IB is the base current, and IC is the collector current. You can write it down in your notes. Now we already know the current gains, okay, for common base, for common emitter and common collector configuration of BJT. We already know the current gains. So let us consider one of the current gain, that is common base current gain. That okay, what is the equation for common base current gain? Alpha equal to IC by IE. So let us consider this. Alpha is equal to IC by IE. Okay, and after considering this you can rearrange this equation and determine IC. So from this equation, what is IC? Alpha into IE. Okay, from this equation, IC is equal to alpha into IE. Alpha into IE. Consider it as equation number 2. I hope you people are writing it down in your notes, because this simplification, this derivation, whatever the relationship between alpha, beta and gamma, so I have written everything step by step, so it will be useful to you. Okay, because when compared to textbook, more number of steps are available in this what I have done. Okay, so alpha equal to IC by IE, you can rearrange, and you will get IC is equal to alpha into IE. So now substitute this 2 in 1. So if you substitute 2 in 1, what do you get? IE is equal to alpha IE plus IB. So here instead of IC, you write this alpha IE. Okay, so IE is equal to alpha IE plus IB you will get. Okay, if you observe here, there is IE term here, IE term here. So you can send alpha IE to the left side. If you send alpha IE to the left side, what do you get? IE minus alpha IE is equal to IB. IE minus alpha IE is equal to IB you will get. So here, if you carefully observe here, there are two common terms. You can take IE common. What do you get? IE into 1 minus alpha is equal to IB. IE into 1 minus alpha is equal to IB you will get. Consider it as equation number 3. Consider it as equation number 3. And from this expression 3, you just determine IE. So what is IE? IB by 1 minus alpha. Write it down. I'll give you a minute. If you are noting it down, I will give you a minute. You people just write it down. If you complete, you can mention complete in the chat box so that I will proceed. If you are completed, just type C. It's okay. No need to write a whole complete word. You can just type C so that I will proceed. So now let us consider one more current gain, that is common emitter current gain. What is it? Common emitter current gain is beta equal to IC by IB. Common emitter current gain expression is what? Beta equal to IC by IB. Now you can rearrange this expression. And what do you get? IC is equal to beta into IB. Okay, so beta equal to IC by IB, that you can rewrite it and you can rearrange the terms and you will get IC equal to beta into IB. Consider it as, I'm sorry, here some number, I will just notations, numbering. Here I have considered I equal to IB by 1 minus alpha as equation number 4. Okay, and in the next slide, here this is 5. Okay, this is 5. So I think I didn't notice this numbering. It's okay. So now here, sorry. This is 5. I will just save it. Now IB equal to IC by, beta equal to IC by IB. That is our common emitter current gain. Now you can rearrange the terms. You can get IC in terms of beta. IC is equal to beta into IB. Now substitute this equation number 5 in 1. So if you substitute this equation number 5 in 1, you will get IE is equal to beta IB plus IB. You will get IE is equal to beta IB plus IB. If IE is equal to beta IB plus IB, so by looking at this expression itself, you can easily say that IB can be taken common and you can get the relation between IE and IB. Okay, isn't it? So I hope you have written. I am just changing this slide. So from this expression, next step is, what is next step? Taking IB common. So next step, taking IB common. 1 second. I will just change the numbering. See, earlier this is 6. The whole sequence will change from now on. See here, I have taken IB common. Okay, I have taken IB common. So what is IE is equal to? IE is equal to beta plus 1 into IB. So what is IB? IE by beta plus 1. Okay. So IB equal to IE by beta plus 1. Now, what is IB expression? IB expression. So IB, go to equation number 3. Okay. For IB, go to equation number 3. IB in equation number 3 is what? E into 1 minus alpha. So instead of IB, I have written, what did I write? From the equation number 3. E into 1 minus alpha. Okay, so I have substituted this 3 in 6. Okay, substituting 3 in 6. Equation number 3. What is equation number 3? Equation number 3 is IB equal to IE into 1 minus alpha. So IE into 1 minus alpha equal to IE by beta plus 1. If you see here IE is there, here also IE is there. What you can do, you can cancel IE. What do you get? 1 minus alpha equal to 1 minus beta plus 1. Okay, so 1 minus alpha equal to 1 by beta plus 1. So you can again rearrange the terms. You can send 1 to this side, the other side. Okay, keeping alpha on this side. So okay, so what do you get? Alpha equal to 1 minus 1 by beta plus 1. This is what you will get. Just write it down. I'm just removing all the ink. If you complete, just mention C in the chat box so that I will proceed further. Just mention C in the chat box as soon as you complete. If my voice is not audible, if there is any disturbance, just inform in the chat box. Okay. So now we have got some relation. What was our title? Relationship between the current gain parameters, isn't it? So I think by looking at this expression, you can see only alpha and beta term is there. So again, you just rearrange these terms. Just simplify this. That's it. Okay. Just simplify this expression. No need to wait for me. You just simplify it. You will get a relation between alpha and beta. So what is it? Alpha equal to beta plus 1 minus 1 by beta plus 1. 1 cancel. And what do you get? Alpha equal to beta by beta plus 1. Okay. So common base current gain in terms of common emitter current gain. Relationship between common base and common emitter current gain is alpha equal to beta by beta plus 1. Consider it as equation number not 6. It is equation number 7, isn't it? This is equation number 7. This is also equation number 7. Okay. So now we have got some relationship between what? We have got relationship between the common base current gain and common emitter current gain. That is our equation number 7. Now rearrange the terms. What do you get? Alpha into beta plus 1 equal to beta. That's what you will get if you just rearrange this equation number 7. Okay. Simply rearranging the terms of equation number 7. Okay. This is what you will get. Okay. Now further simplify it. So what was the above equation? Alpha into beta plus 1. Just multiply alpha with beta and 1. What do you get? You will get alpha beta plus alpha is equal to beta. So alpha beta, so there is a beta term here and there is a beta term here. So I have sent betas on one side. So alpha beta minus beta is equal to minus alpha. So here take beta common. You will get alpha minus 1 into beta equal to minus alpha. So take minus common. On the left hand side, you will get minus of 1 minus alpha beta equal to minus alpha. Cancel minus minus, you will get 1 minus alpha beta equal to alpha. So beta equal to alpha by 1 minus alpha. So this is the relationship between the common emitter current gain and common base current gain. So simply I have modified the above equation 7. That's it, to get equation number. This is not 7 here, it is, this equation is 8. This is equation number 8. Okay. So we have got some expression for alpha and some expression for beta. Okay, in terms of alpha, in terms of beta, beta in terms of alpha that we have got. One more parameter is left over, that is common collector current gain parameter is left over. Okay, so for that, I hope you might have written this, you might have completed writing. Okay, I'm going to the next slide. Okay, so I'm going to consider now the common collector current gain parameters, that is gamma is equal to IE by IB. Expression for the common collector current gain parameter is gamma equal to IE by IB. So this above equation, you can rearrange the above equation and you can rewrite this equation as IE is equal to gamma into IB. So again, once again, I will just change the numbering of this expression because this number should be 9 and this number should also be 9. Okay. So this is it. Gamma equal to IE by IB. So IE is equal to gamma into IB. That is our expression 9. Now substitute this 9 in 1. 1 is the first equation. Relationship between collector current, emitter current, and base current. That is our first expression. So the first equation. So substitute 9 in first equation. So what is IE? IE instead of IE, write gamma IB equal to IC plus IB. So you can see on the left side and right side, IB is common. Okay. So you can send IB term on one side, isn't it? You can send IB term on one side. So you will get gamma into gamma IB minus IB. You can take IB common, gamma minus 1 into IB equal to IC you will get. But we want gamma value. Okay. So we don't want any gamma minus 1. So simply what I have done is simply I have sent IB to the denominator here in the next slide. So I have sent IB to the denominator. So IC plus IB by IB I have got. Now I have considered equation number 4. So what is equation number 4? It is beta IB. So that is IC is equal to beta IB. Okay. So equation number 4. IC is equal to beta IB. So that is, I think it's not equation 4. It is our equation number 5, I think so. Is it 4 or 5? You can mention in the chat box because I have for two terms I gave the same numbering. So I will just check here. Equation 5. Equation 5. IC is equal to beta IB. I don't know whether it is visible to you people or not. So you can see here equation 5. IC is equal to beta IB. So instead of IC I have written beta IB. Okay, that's it's correct. So numbering is correct. So gamma equal to beta IB plus IB by IB. So you can take IB common in the numerator and you can cancel numerator and denominator, isn't it? You can do that. Okay. So I hope you have written. So I have taken IB common. I have cancelled numerator and denominator IB. I have cancelled numerator and denominator IB. If I cancel, what do I get? Gamma equal to beta plus 1 by 1. And we already know, no need to write the denominator 1. So what is gamma equal to? Beta plus 1. So the common collector current gain is expressed in terms of common emitter current gain. Okay. So these are all the relationships between the alpha, beta and gamma. Common collector, common emitter and common base current gain parameters relationships. Okay. So I hope you have understood. If you are listening to the class, okay, if you are listening, you might have followed what I have been explaining it to you. Okay. Now let us see the configurations of BJT and characteristics of BJT. Okay. So configurations and characteristics of bipolar junction transistors. Next title, write it down. Configurations and characteristics of bipolar junction transistors. So at the beginning of the previous topic, I have already told you there are three configurations of bipolar junction transistor. Those three configurations are common base configuration, common emitter configuration and common collector configuration. Common base configuration usually it is denoted by CB, common emitter is denoted by CE, common collector is denoted by CC. Just write it down. Okay, I hope you might have written. As soon as you complete, you just mention, just type C so that okay, so that I can proceed further. Okay, so that I can proceed further, you just type C in the chat box as soon as you complete. So these are the three configurations: common base configuration, common emitter configuration, and common collector configuration of bipolar junction transistors. Okay, so these configurations, they offer distinct advantages in terms of voltage gain, current gain, and impedance characteristics. Okay, so they offer distinct advantages in terms of voltage gain, current gain, and impedance characteristics. So now let us start with one by one configuration. Let us start with one by one. Let us start with common base configuration. Okay, so let us start with common base configuration. So this is our common base configuration. So this is our BJT. You can draw it if you want. You can draw it. This is our BJT. So here base is common to both input as well as output. Okay, you can draw it. I'll give you a minute. You can draw it. Roughly you can draw. Okay, so I will be just giving the explanation. You just draw. While drawing, you just listen. Here, this base terminal, so it is shared by both the input as well as output. Okay, so this sort of common base configuration. Okay, this sort of common base configuration. Where is my cursor? This sort of common base configuration, it is used for the circuits where you need high voltage gain and low input impedance. Okay, so the circuits wherever you need high voltage gain and low input impedance in such circuit. Okay, what to say, this sort of common base configuration is used. So input is connected to the emitter, output is connected to what? Collector. Okay, here input is connected to the emitter and output is connected to the collector. Okay, and this circuit, as I've already told you, it gives out high voltage gain. Why? Because its input impedance is low. So you can see a resistor here. Only resistor is shown at the input side. So input impedance for this common base circuit will be low. Okay, input impedance will be low and output impedance will be high. Okay, so output, this is our load RL. Okay, so output impedance at the collector will be high. So input impedance at the emitter will be low and output impedance at the collector will be high. So this circuit can give us high voltage gain. But if I want current gain, this circuit is not applicable for current gains. Okay, it won't provide any current gain. Okay, so common base means, as I hope you already know, common base means in common base configuration, the current gain that can be obtained is alpha. Okay, so here current gain configuration is not provided. Okay, alpha value you can't determine for this circuit. Okay, even though it is common base, it does not provide any current gain. Okay, so these sort of circuits, they are ideal for impedance matching in high frequency amplifiers and radio frequency circuits. Okay, so this sort of common base configuration can be used for, okay, they are applicable for impedance matching in high frequency amplifiers and radio frequency circuits. Okay, this sort of common base circuits, they ensure there is maximum power transferred from the input to the output. Okay, maximum power is transferred from input to the output for this sort of circuits. Okay, now let us see the characteristics. Okay, let us see the input characteristics. So, input characteristics for this common base configuration is this. So, this is you can see some two curves are there. Two curves are here. So, the input characteristics are drawn between emitter current and emitter base voltage, keeping the collector base voltage constant. Okay, collector base voltage is kept constant. So I'll go back to the circuit. So if you see here, what are our input parameters? V in, input side current is IV. Input side voltage is also VB. Output side is IC, V out. Okay, so of course VC and VB, okay, they are connected to the base, common base. Okay, so here, so we can say voltage between collector, I'm sorry, here this is VC, it's not VCE, it is VCB. Okay, so no. So I'm sorry, I didn't notice here. This is base and collector voltage. Base and collector voltage. Here there is a mistake. I'll just rectify it 1 second. All of you, I hope you might have already drawn this diagram, isn't it? If you have drawn it, you just change it. I didn't notice that because this emitter voltage will not exist on the output side. Emitter is on the input side, isn't it? So this is VCB. This is not VCE. So keeping VCB constant. Okay. So here what we are going to do is keeping VCB output voltage constant. Okay, this is output. These three are input side. You can see, of course, they are this VBE and VCB are connected to the base, but VBE anyhow it is on the input side only. Okay, so V in, VIE and VB are input. IC, V out and VCB are output. Okay, output side. Okay, so keeping VCB constant, I'll just erase all ins. Keeping VCB, where is my cursor? Keeping VCB constant, it is on the output side, okay? Keeping VCB constant, varying IE, okay, varying IE and VEB, means VBE, okay, varying IE and VBE, I can get input characteristics. Now let's go to the characteristics. Input characteristics. Okay, all of you write down input characteristics. Input characteristics. IE versus VEB. Okay, IE versus VEB. VEB means what? VEB means emitter base voltage. IE means emitter current. Okay. So what did we assume constant? Collector base voltage is maintained constant. Here you can see 10 volts. Here you can see 0 volts. Collector base voltage constant. So by varying VEB, IE will vary. Okay. So these are the characteristics that you will get. These are the input characteristics. So I hope you have drawn it. So now let us see the output characteristics. These are the input characteristics, output characteristics. So output characteristics. So output characteristics are drawn between what? Collector current and collector base voltage for the given IE constant. Okay, emitter current, keeping emitter current constant. So what is emitter current? What is it? So this is it. Keeping IE constant, I will just erase all the inks. So keeping IE constant. Here we are assuming IE as input side current as constant. Okay. Output characteristics are drawn between IC versus VCB. Okay. IC versus VCB. So these are the output parameters, isn't it? IC, Vout and VCB. So VCB, so as VCB vary, automatically IC will vary. And we have assumed some, we will assume some value for IE. IE is kept constant. So for different IE values, output characteristics, this is it. So for some IE value, so this is it. I will just consider pen. For some IE value, assuming IE constant, varying VCB, this is B. Okay. Varying the VCB, IC will vary. So that for some value of IE, you may get this. Okay. And for some value of another value of IE, the characteristics will change. So you just vary the IE, you assume some value of IE. Okay. So based on the IE value, the characteristics of the IC and IC with respect to VCB will vary. And if you observe carefully, for up to when IE is very low, you can see IE is gradually increasing. Okay, when IE is emitter current is low, initially as collector base voltage increases, IC will increase. After that, it is becoming constant. Okay, and similarly, when IE is varied to some other value, collector current is increasing. After that, it is becoming constant. Okay. So up to certain value, certain low values of VCB. Okay. For certain low values of VCB, okay, IC is varying. After beyond that value, IC is becoming constant. Okay. Even though VCB is varied, VCB, see VCB is varied, VCB is increasing. What about IC at this value? This is some IC value. What about IC at this? IC is constant. Parallel lines means they are constant. Parallel means constant. Okay. So these are the output characteristics of common base configuration. Now let us go for the next configuration. Let's go for the next configuration. Common emitter configuration. Common emitter configuration. So you can see this is our BJT. This is our BJT. This is our emitter, which is common to both input and output. So what are our input parameters for common emitter configuration? Input parameters are Vin, base current IB, base and emitter voltage between base and emitter. Okay, so base and emitter voltage VBE. What are our output parameters? These are our input parameters. Okay, for common emitter configuration. What are our output parameters? Output parameters are collector current, V out, and yeah, VCE, collector emitter voltage. Okay, VCE. Okay, these are our output parameters. These are output parameters. This one, and this. Input parameters are IB, Vin, VBE. So this common emitter configuration, it usually provides great gain properties. Okay, it is most commonly used configuration among these three configurations. What are the three configurations? Common base configuration, common emitter configuration, common collector configuration. Among these three, most commonly used configuration is common emitter configuration. Okay. So here emitter is shared by both input and output terminals. Okay. So this sort of configuration, it provides significant voltage gain. Okay. So you can use it for amplification, and this voltage gain that is provided by this sort of configuration will depend on how much is the load resistance. Where is our load resistor? Isn't it? This is our load resistor. Okay. So how much voltage gain will be there? That will depend on the load resistance value as well as transistor properties. Okay. So as I have told you just now, it gives us significant voltage gain. So it can be used for amplification. So it not only gives us voltage gain, it also gives us current gain. So for common emitter configuration, what is our current gain? We have already discussed, that is beta. For common emitter configuration, the current gain is beta. So it common emitter we have seen earlier, common base configuration gives us only voltage gain, whereas common emitter configuration gives us both voltage gain as well as current gain. Okay, so this common emitter configuration, it can amplify weak input signals into stronger output signals. So even if a weak input signal is given, it can give out a strong output signal. So this common emitter configuration has moderate input and output impedance. Means it will usually have moderate input impedance as well as output impedance. There is my cursor. This is it. It has moderate input impedance and moderate output impedance. Okay. So of course in this diagram only resistors are shown. Okay. If reactance is 0, resistance is equal to impedance. I hope you know that. So this is this common emitter configuration. It can be used for many amplifying circuits. Okay, so since it is providing voltage gain as well as current gain, it is used for audio amplifiers, signal processing circuits. Okay, and in other applications where strong amplification is required. Okay, so this is about common emitter configuration. Now let us see the characteristics. So let us start with the input characteristics. So in order to determine input characteristics, so what are all the parameters that are there on the input side? Let us check here. What are the input parameters? Okay, there is my cursor. Yeah, input parameters are IB, VBE, of course VIN. Output parameters IC, Vout and VCE. So to determine input parameters, some output parameters should be kept constant. To determine input parameters, VCE is kept constant. Okay, to determine input parameters. Now let us see. Okay, so input characteristics of common emitter configuration. Okay, input characteristics of common emitter configuration. So these are the input characteristics. So what did I assume? I have assumed some constant value for VCE. So here in this diagram, I am showing you three different constant values. Why cursor is not so clear? Yeah. So for some value of VCE, you can see initially, even though VBE is increasing, okay, VBE is increasing, IB remains 0. You just observe here in this diagram. Initially at this instant, both VBE and IB are 0. Now VB is gradually increasing. But what about IB? IB is still 0. IB is still 0. Up to what voltage when VB is equal to 0.5 volts? Okay, until VB equal to 0.5 volts. Okay, until VB equal to 0.5 volts. Okay, IB is VB is 0.5 volts. IB is 0. Once VB is reached 0.5 volts, as VB increases, IB also increases for some value, of VCE, for some constant value of VCE, as VB increases, IB increases. For some value of VCE, some other value of VCE, as VB increases, IB increases. For some other value of VCE, as VB increases, IB increases. Okay? I hope you are able to follow. Don't worry about this. This represents that. This represents this symbol, this symbol represents what to say. If I want to write 0 to 10, if I want to write 0 to 10, so I should write 0, 1, 2, 3, 4, 5, 6, 7, and so on. So instead of writing like that, I'll put some symbol. I will write 9 and 10. So in between some terms are there which are missing. Instead of writing them, what did I write? I have put this symbol. So that's the meaning of this symbol, nothing else. Okay. So the meaning of this symbol is that in between we are not writing the sequence. Okay, here it is 0, here it is 0.5. Okay, in between some 0.1, 0.2, 0.3, 0.4, 0.4 must be written here. We didn't write them. Instead of that, we have simply put some symbol. The meaning of this symbol is in between sequence is there. We did not write the sequence. We have just skipped that sequence. That's it. That's the meaning. Nothing else. Okay. So don't worry about this. Okay, no need to worry about this. Even if you won't draw this, it doesn't matter. You can put a straight line. You can put a straight line. It doesn't matter. Okay, so we have assumed some constant value of VCE. We have assumed some constant value of VCE, and we have got the relation between VBE and IB. Okay, for some other constant, we have got the relation between VBE and IB. For some other constant value of VCE, we have got another relation between VBE and IB. I hope you have drawn. Meanwhile, I was giving explanation. You might have completed drawing. Okay. So let us proceed further to the output characteristics. So for the output characteristics, let us go back to this circuit. So we have to assume some input parameter constant. So I am assuming input current IB constant. I will just erase all links. So this is our IB base current. I am assuming it as constant. I am assuming it as constant. Okay. Okay. So assuming input parameter current constant. Okay. So what are my output currents? common emitter, isn't it? Okay, output currents are IC and VCE. Okay, IC and VCE. Okay, IC and VCE. So let us see the characteristics. Output characteristics. Okay, so on second. So here I have in the theory, whatever theory I have written in the theory, instead of writing collector current, I have written emitter current. This is collector current. So it is in capitals. This is selected sentence case. Okay, so here it is. I see. So in the diagram, so there is a mistake here. So this is IC, not IE. This is my pen. These are the output characteristics. Print mistake is there. This is IC. Okay, collector current versus collector emitter voltage. Okay, assuming IB constant. So IB, assuming when IB is 0. Okay, when IB is 0, so when VC is varied, IC will vary. These are the characteristics. Again, when IB is 40 microamperes, these are the IC and VC characteristics. When IB is 80 microamperes, and so on. Okay, so this region where the characteristics are not available, that is known as saturation region. Where the characteristics are available, that is known as active region. Okay, so this straight line you can see, this slant slope like line, that is our active region. Because as up to this, you see, up to here, as VC varies, IC, this is IC, sorry, IC is varying. After that, IC is becoming constant. Okay, after that, IC is becoming constant. Up to this, as VC increases, IC increases. Similarly, up to this, as VC increases, IC increases. Therefore, that is our active region. Means, as one parameter varies, another parameter should also vary. Okay, so this is IC. There is a print mistake here. So IC versus VC. These are the characteristics. I will just erase all inks and I will just make sure this looks like C. Now draw the output characteristics. So here for plotting the output characteristics, we are assuming base current constant. We are plotting the graph between IC and VCE. So this region, if you see here, here it is mentioned cutoff region. Cutoff region means below base current, if you see base current, for base current 0, these are the characteristics. You can't reduce further the base current, isn't it? That's why the characteristics below this, where below the characteristics where IB is equal to 0, that region you call it as cutoff region. Means characteristics won't lie in this region. Now let us proceed further. Okay, let us proceed further. Let us go for the next one, that is common collector configuration. So here in this, you can see this is our emitter, this is our base, this is our collector. So here you can see the collector is common to both input as well as output. Okay. So the input voltage is what? Input voltage is not mentioned here. I will write it down, VBC. And this voltage is VEC. Isn't it? This voltage is VEC, this voltage is VBC. So just draw this. Meanwhile, I will give the explanation for this common collector configuration. So here, this common collector configuration, you can even call it as emitter follower. Okay, you can call common collector configuration as emitter follower. Okay. So here, collector is common to both input and output. So this sort of common collector is useful for matching impedances in the circuits or for buffering the signals. So if I want to buffer the signals, I can go for common collector configuration. If I want to match the impedances for the given circuits, I can go for common collector configuration. So it can provide the voltage gain of about 1, meaning it keeps the input signal voltage at the same level while transforming the impedance. Okay, so while transforming the impedance, this common collector configuration keeps the input signal level same. It won't change the input signal. Okay, and this common collector configuration will offer high current gain, which is similar to your common emitter configuration. And this current gain value will be slightly less than these transistors beta. Current gain, that is common collector current gain is what? Gamma. Gamma value will be slightly less than the beta value, but still it is more significant value, and it is still good for driving the loads that need more current. Okay, so the loads that require more current, for such loads, this common collector configuration can be used, as it provides us sufficient current gain. Okay, and this common collector configuration has high input impedance and a low output impedance, and it can be used for buffering applications where it can connect high impedance sources with low impedance loads. Okay, so these sort of circuits, they can be connected for the circuits where the source has high impedance and load has low impedance. Okay, and common collector configurations, if I am using common collector configurations, then I can make sure that there will be minimum signal loss, and signal distortion will also be minimum. Okay, so that's the advantage of this common collector configuration. So this is about common collector configuration. Now let us see the input and output characteristics. So input characteristics. So if you see, what are all the parameters on the input side? IB is there, input voltage is there, and VBC is there. Okay. And what are the outputs? Output, I didn't here simply output voltage I can say. Voltage, emitter collector voltage and emitter current. Okay. So these are the input and output parameters. I will just erase all ins. So if I want input characteristics, some parameter on the output side should be constant. So this is our VCE current voltage, sorry, VCE voltage. I am assuming it as constant to determine what? Input characteristics. To determine input characteristics. So what is this? This is VBC. So I am going to plot the characteristics between VCB or VBC and IB, assuming VC is constant. Okay, assuming VC is constant, I am going to plot the characteristics between IB and VBC. So let us see the input characteristics. Okay, let us see the input characteristics. So input characteristics are these. Is there cursor? Yeah. So you can see VBC and IB, and I have assumed some value of VCE, that is 1 volt. When VC is kept 1 volt and when VBC is varied, you can see as VBC is increasing, IB is what? From 0 to 1.5, it is 0. At 1.5 volts, when VBC is 1.5 volts, IB increases as VBC increases up to certain value. After that, it is becoming constant. Similarly, when VC is 2 volts, as VBC increases, IB is 0, from 0 to 2.5 volts. Okay. So when VBC is until VBC reaches 2.5 volts, IB is 0 here. Okay. IB is 0. After that, once 2.5 volts is reached, as VBC increases, where is my cursor? Yeah. As VBC increases, IB gradually increases up to certain value. After that, it becomes constant. Okay. So these are the input characteristics. Assuming VCE constant, as VBC varies, how IB is vary, you can see here. Just draw it quickly. So someone wants to look at the theory. Okay, I didn't notice that. Okay. So don't go through the unnecessary message sent by some unknown person. Some game hacker is mentioned in the chat box. Don't go through those messages. I didn't notice till now. Okay. So some people, I don't know why they join this. This is lecture content and okay, whatever. I hope you have drawn it. I was just waiting for you people to complete. Next, output characteristics. Okay, so let us see output characteristics. So in order to determine the output characteristics, so we have to assume some constant parameter on input side. So let's go back to the circuit. Okay, let us go back to the circuit. So here, common collector, isn't it? Here, where is my cursor? Yeah. So I'm assuming input parameter IB constant. Okay, input parameter IB constant. Okay, and I will vary this VCE. Okay, so I will plot the characteristics between IE and VCE. Okay, characteristics between IE and VCE, assuming what? Base current constant. Okay, assuming base current constant. So this is it. These are the characteristics. So you can see this is VCE, this is IE. Okay. So when IB is 0, so as VCE is increasing gradually, IE also increases, and for low values of VCE, okay, for some value of VCE, okay, so IE increases. After that, IE becomes constant. Similarly, for some other value of IB of around 20 microamperes, as VC increases gradually, IE also increasing up to certain value. After that, IE is becoming constant. Similarly, for some other value of IB, that is IB equal to 40 microamperes. Okay, so IE increases, after that it becomes constant. So when the characteristics that you get for IB equal to 0, the region below it is, you call it as cutoff region, because IB is already 0. Below IB value, you don't require any value below IB. So this region you call it as cutoff region, and the region where characteristics are not at all obtained here. Okay, so that region you call it as saturation region, and the active region is the region where, okay, the region where both both IE, as VC is varied, IE also varying. So I can say this line, it is the active region. Next, this is the active region. Up to here, it is the active region. That's it. Active region means both parameters should vary. So that is known as active regions. In this diagram, only one line is mentioned as active region. This only line is mentioned as active region. But depending on how IB value varies, depending on IB value, whatever may be the IB value, if IE and VC both are varying at a time, that region you can call it as active region. So just draw the characteristics. If you complete, mention C. So someone has mentioned there is disturbance. I didn't know that. Let me check. Because I am also one of the viewers. No, Mama, there is no disturbance because I am also, I have also joined this session with some other email ID, as you people have joined my class. So it's a clear voice. If there is a disturbance, I will also get I have 3 devices connected at a time. Okay, not only single device, I have connected with 3 devices in order to know how my class is going on, how my voice is, whether my voice is audible or not. Maybe because of the rain in your area, signal is not, signal issue is there. That's why there may be disturbance to you. Okay, so on my side, it's okay because my internet speed is around 300 megabytes or gigabytes or whatever. 300 GB I think so. I have already, before starting the class, I have checked the internet speed. So it's high speed internet. So because of the rain, okay. So I hope you have completed drawing the characteristics. Okay, some unnecessary people, they join the class just to disturb the online classes. I have already seen such people. This is not new to me. So don't uh, read those messages which these unnecessary people are sending. Okay, you just concentrate on the lecture and note it down whatever is required or useful to you. That's it. Okay, don't worry about the messages that were sent. They don't have any other job. Okay, that's why they have entered this session and they are writing unnecessary messages. Okay, on my side there is no disturbance. I have checked. Okay, so please, maybe because of the rain, you don't have a good signal in your area. Okay, now let us see the applications. BJT. I have already discussed the applications while discussing about the configurations. So it can be used as an amplifier. It can be used as a switch. It can be used as a signal oscillator. Okay. Okay. So this BJT, it can be used in logic circuits. What are the logic circuits? That's another topic. Okay. So it can be used in the logic circuits, clipping circuits. It can be used as a demodulator. It can also be used as a detector. It can be used in temperature sensors. So these are all the applications of BJT. Okay, one more topic is there. I will discuss the topic and conclude today's session. Some person, I don't know who, he has mentioned to teach in Telugu. This whole, see, if one channel is there, the language for that channel should be the same language. Okay, so I have been teaching in English, so I can't use Telugu language to teach the lecture. So whoever wants Telugu lectures, better you can go for the YouTube channel. Okay, so who deliver the lectures in Telugu. But for me, it's not possible because my channel is um, in my channel only English lectures are being delivered. Even someone asked me once for Hindi, but for that I have to start another language channel, Hindi language channel. I can't speak in Telugu. Of course, I can deliver lectures in Hindi. For that, I can't deliver Hindi lectures in this channel. So let us go for the next one. This is the last topic in this session. Elementary treatment of small signal common emitter amplifier. Just write it down. Okay, so amplifier is what? It can amplify weak electrical signals into strong one by increasing the power level of the weak input signal. So what is an amplifier? Amplifier is a system that can amplify weak electrical signals into what? Strong electrical signals. Okay, by increasing the power level of the weak input signal. Okay, so this amplifier, it can amplify current, voltage, and power. Okay, it can amplify current, voltage, and power. So let us see a schematic diagram. So this is it. You can see here in this diagram, you can see there is an amplifier here. To this input signal is given and you are getting an output signal. So Vi is the input, V0 is the output. So this is a given input signal which has been amplified and it have got a larger signal here. Okay, so for this amplifier, it needs some energy to perform its, when input is given, it has to produce the output. So it needs some electrical energy. So that electrical energy that is given here as DC supply voltage is our input. No, sorry, not input. It is the energy source for the amplifier to perform its function. When input signal is given, it has to produce the output signal. So it needs some energy. That is our DC supply. Voltage is our energy. So just draw it. So I'm not showing you the theory because while showing the diagram, I have to give the explanation. So that's why I'm unable to show both theory as well as diagram. Someone wanted me to show the theory on this PPT. Okay, next time if I take the class, I will make sure I just write the key points on the PPT and I show it to you. Next time I will do that. Okay, I don't know whether you have completed. Completed, maybe. Okay then. So now this amplifier, what does it do? What does it do? It takes the weak signal. Okay, it takes the weak signal. Okay, and amplifies it. Okay, to a stronger signal. Okay, so it can amplify current, voltage, or power. Okay, so amplifier has three basic quantities. What are those three basic quantities? One is gain. I'm unable to find my cursor. Gain A. Gain is denoted by A. Input impedance and output impedance. Amplifier has three basic quantities. One is gain. Another one is input impedance. And one more term is output impedance. So to be more specific, you can write Zi as the input impedance, Z0 as the output impedance. Okay, these are the three basic quantities. So what is meant by gain? Gain is a small signal, okay, provided by the amplifier, okay, when input signal is given, okay. So gain of a small signal amplifier is the amount by which the amplifier amplifies the given input signal. So when input is given, okay, when input is given, here input is given, output is to be produced. So when input is given, output is to be produced. So how much amount of amplification takes place? Okay, so if you see here, this is the peak value of the input signal, and here this is the peak value. So for how much amplification, how much amount of amplification that has been taken place. So I think according to this diagram, whatever roughly I'm drawing, so this much amount of amplification has been take place. So this much amount of amplification can take place. Therefore, that is the gain value. Okay. So what is gain? So gain is what? It is the amount. Oh, my cursor is. Where is my cursor? It is the amount by which the amplifier amplifies the input signal. This is the amount by which, okay, how much amount of input signal has been amplified. That is known as gain. Okay, how much amount has been amplified, that is known as gain. So simply if you want to uh, get any relationship, if you write any equation for gain, so gain is the ratio of output to the input. Cursor. Gain is the ratio of output to the input. Okay, and it does not have any units. Gain does not have any units. It is the ratio of output to the input. There are three types of BJT gains, bipolar junction transistor gains. Three gains are there. One is voltage gain, current gain, power gain. These are the three gains. Write it down. Okay. Gain is the amount by which the amplifier will amplify the input signal. Okay, so this gain is nothing but it is a ratio of output and input, and it can be of three types: voltage gain, current gain, and power gain. Now let us see the expression for this voltage gain. Simply I have told you it is the ratio of output by input. Therefore, what is voltage gain? Its notation is AV. Okay, voltage gain. A means gain, V means voltage. So A is V naught by Vi. V naught means output voltage by input voltage. Voltage gain is the ratio of output voltage by input voltage. I hope you have written. Okay, so current gain AI. AI, it is the ratio of output current by input current. That's it. Similarly, power gain. It is the ratio of output power by input power. Okay, so if you want to write the power gain in terms of current gain and voltage gain, simply multiply the current gain and voltage gain, you will get the power gain. Okay, multiplication of current gain and voltage gain will give us the power gain. Okay, so if you have small signal amplifiers, you can even call them as voltage amplifiers. Small signal amplifiers are also known as voltage amplifiers. So this power gain, it can be expressed in decibels. Okay, units. Decibels are the units. It can be expressed in decibels, and decibels. So I can write here units as decibels. Okay, power gain can be expressed as decibels. So as I've already told you, there are three types of configuration: common emitter, common base, and common collector. Among these three, most commonly used configuration is common emitter configuration. So common emitter amplifier configuration is the most generally used amplifier configuration. Okay, which is mostly used for voltage amplification. Okay, so I have the circuit for this. I have the circuit for this common emitter. amplifier configuration, which is used for voltage amplification. So this is the circuit. So in this circuit, there are many parameters. You can see many parameters are there. You can draw this circuit. You can see R1 parameter is there, C1 is there, input voltage is there, R2 is there, RE, C2, RL. Okay, of course, collector current. So this is collector, it is not mentioned here, of course. This is C, this is B, write it down, it is not mentioned here. This is E. Okay, so this is common emitter configuration. So collector, base and emitter. So here, so this is in this this is an common emitter amplifier. You should call this circuit as common emitter amplifier circuit. So here R1 resistor is there. The purpose of R1, the purpose of this R1 resistor is to provide forward bias. Okay, and R2 is used to develop the bias. Okay, R1 is used for forward bias. R2 is used for the development of the bias, to develop the bias, and RL is the load resistor. Okay, RL is the load resistor. And if you see one more resistor, RE. RE is known as thermal resistor, or you can call it as thermal resistor, which is used for thermal stability. Thermal means temperature. So in order to stabilize the temperature, this resistor RE is used. So R1 is used for forward bias, RE is used to develop the bias, RE is used for thermal stability. And if you see here, there is one capacitor here, C1. C1 is the capacitor which is used to separate AC signal from the DC biasing voltage. Okay. So what is our input signal? If you observe here, this is our AC signal. Okay. So this C1 is used to separate AC signal from the DC biasing voltage. And this C1 is also known as coupling capacitor. C1 is known as what? Coupling capacitor. I am erasing all the inks. Okay, C1 is known as it is used for separating the AC signal from DC biasing voltage, and it is also known as coupling capacitor. So now here this is our input that is applied across what? Base and emitter junction. Okay, so input is applied across base emitter junction. So when input is given across base emitter junction, what will happen is forward bias will occur at this junction. Okay, and what will happen? The voltage will gradually start to increase. Okay, and when voltage gradually increases, automatically the electrons flow from emitter to the base will also increase. Okay, and we know collector C collects the current from the base. So the collector will collect all the electrons from the base. So collector current will also increase. So what is happening here? When you give input voltage V in, what will happen? When input voltage is given, that is voltage, when voltage between base and emitter is increasing, the electrons moving from emitter to base is increasing. So collector current gradually start to increase because collector collects these electrons from the base. Okay. So this increase in the collector current will cause the voltage drop across the load resistor. So when collector current is gradually increasing, voltage across the load resistor will decrease. Therefore, during the next negative half cycle, during positive half cycle, voltage across the current collector will gradually increase. Okay. So when but during the negative half cycle, we know since we are giving the AC, during positive half cycle, the whatever voltage drop will occur across the load, collector current will gradually increase during the positive half cycle of your input. Okay, so I will draw that. This is our input signal. Let us assume sinusoidal input we are giving. So during, I didn't draw uniformly, but I will try. Okay, I will try. This is it. So during positive half cycle, what is happening? Voltage between base and emitter will gradually increase. So electrons are emitted by this emitter into the base. Okay, and the electrons from base are collected by this collector, and collector current gradually increases, and voltage across the load resistor will start to decrease. Okay, voltage across the load will start to decrease. That is during the positive half cycle. Okay, during the negative half cycle, forward bias voltage will start to decrease. Okay, so earlier the forward bias voltage was increasing gradually. Now the forward bias voltage at the junction will start to decrease, emitter base junction. Okay, so the forward bias voltage across this emitter base junction will start to decrease. Okay, and so as the forward bias voltage is decreasing, what will happen? Collector base junction. Okay, collector base junction voltage will also start to decrease. Okay, when collector base junction voltage is decreasing, collector current IC will also decrease. Okay, IC current will also decrease. This is during negative half cycle. Okay, and this the voltage gain of this common emitter amplifier, it usually varies with the signal frequency. Means as signal frequency varies, the voltage gain of the common emitter amplifier will also vary. Okay, so now let us see the characteristics. Okay, the curve drawn between voltage gain and signal frequency of this amplifier. Let us see those characteristics. So I have already prepared the material. So now you can see here I have 3 diagrams. So now you can see in this diagram, this is low frequency region. This is high frequency region. This is the mid frequency region. This is the output voltage versus frequency. Okay, or voltage gain AV versus frequency. So this mid frequency region, what you can see, it is the ideal frequency region. Okay, so but this curve, what you can see, this curve, inverted U-shaped curve, that is the frequency response of practical amplifier. Okay, that is the frequency response of practical amplifier. So now if you consider low frequency region, okay, so let me write here frequency FL. This is FL from here to here. Okay, this is FH, let us use. Okay, this terminal is FH, this terminal let us assume FL. So at low frequencies, that is frequency less than FL, the reactance of the coupling capacitor C2. Okay, C2 is the coupling capacitor which is connected across the resistor RE. This is it. The reactance of the coupling capacitor C2 is relatively high. Hence, very small part of the signal will pass through the amplifier stage to the load. Means very small signal will flow from the amplifier to the load. Where is our load? This is our load. Where is my cursor? This is our load. Okay, for low frequencies. Okay, so and this common emitter will shunt the RE. Okay, common emitter will shunt the RE. Shunt means parallel connection. Okay, so if you see C2 is connected parallel to RE, so the common emitter will shunt the RE effectively because it's large reactance at low frequencies. Okay, so it's a reactance of this Ce2 is connected parallel to Re. So the overall reactance will become very large. Okay, overall reactance will become very large at low frequencies. Therefore, very small signal will pass to the load. Okay, so what will happen at low frequencies? There will be voltage drop. Okay, voltage gain will be very very low. Okay, voltage gain will be very very low. Now let us consider high frequencies. Okay, high frequencies. So frequency above FH. This is FH. So these are the high frequencies. At high frequencies, the reactance of the coupling capacitor C2 is very small. It behaves as short circuit. So at high frequencies, what will happen? The reactance of capacitor C2 will be very small. It acts as what? Short circuit. Okay, it acts as short circuit. This will increase the loading effect of this amplifier and serve to reduce the voltage gain. Okay. So if there is any reduction in the voltage gain, that can be reduced. Reduction in the voltage gain can be reduced. So at high frequencies, okay, not reduction in the voltage gain, but the voltage gain itself will be reduced if the capacitor acts as a short circuit. So at high frequencies, the capacitive reactance of base and emitter junction is low. Okay, so at low frequencies it was high. Now at high frequencies, this reactance is low. Okay, this reactance is very low. Okay, this because of this, what will happen is the base current IB will increase. Okay, and when IB increases, what will happen is the beta will decrease. Beta means what? Current gain value will decrease. Okay, and at high frequencies, because the reactance is low and beta is also low, therefore voltage gain is also low. So voltage gain is low for both low frequencies. Voltage gain is low for both low frequencies and high frequencies. Okay, voltage gain is low for both low frequencies and high frequencies. Now for mid frequencies, that is when frequency is varying from FL to FH. For frequency between FL and FH, for mid frequencies, the voltage gain of the amplifier will remain constant. Okay, the voltage gain will not change. The effect of this coupling capacitor C2, its effect will be such that voltage gain will be maintained constant. Okay, voltage gain will not change for the mid range of frequencies. Okay, so as the frequency increases within this range, reactance of the coupling uh, capacitor gradually decreases and tends to increase the gain. Okay, so this capacitance value gradually increases, and because of the decrease in this capacitance value, what will happen is the capacitance value means the reactance of the capacitor. As it decreases, the gain will gradually increase. Okay, so FL and FH, you can call them as low corner frequency and high corner frequency. This FL, FH, it is available here. Say, okay. You can call these two FL and FH as low corner frequency and high corner frequency. Here it is mentioned lower cutoff and higher cutoff frequency. You can even call them as low corner and high corner frequencies, which are the gains that fall for the circuit at high as well as low frequencies. Okay. So these frequency points are also, you can call them as decibel points. FL and FH, you can call them as decibel points. Okay, if I want to determine the bandwidth, okay, if I want to determine, you can see here it is mentioned. What is it? A cursor? Yeah. If I want to determine the bandwidth, okay, so simply I can take the difference of FH and FL to get the bandwidth. Okay, so somewhere it is written, somewhere I have to check. Mm. So this is the bandwidth is given by FH minus FL. This is the bandwidth. Okay, that is FH minus FL. So I hope the diagram that you have to draw, you can draw this this, or you can draw this, and you can mention here FL and FH. FL, you can mention here FL, FH, okay, and here you can mention bandwidth. Okay, here you can mention bandwidth. You can draw this diagram. As soon as you complete mention, I will just conclude. That's it. It's over. Today's session is over. You can draw this diagram. If you complete it, just mention. I will just quit the class.
Mommy, mommy.
Okay, completed. Okay then.